So we're going to look at the wire sizing article that's in Moodle. And you guys can read this and try to make sense of it. Work through the math, because it's pretty important, and you'll probably have to do some of this on the NAB step. So again, we were just talking about module specs and inverter specs, and here they give some examples and have all the details here. And then what we're going to go through the process of sizing wires for the array side of this system. Before we dive into that, do I want to talk about? No, we'll go through this, and then if I have time, I'll give you a couple of footnotes, because it's not as commonly done this way anymore, but this is critical that you do know, because everything's kind of based on being able to size the wire correctly. So again, we have over on the specs, for the module, you have short circuit current. And again, we talked about finding out how many modules are going to be in your array. And when you're putting modules in series, they're just like batteries. You know, they're going to add voltage, but current is going to stay the same. So if you have a single string, you're only going to be looking at the stated current of an individual module. So voltage is going to add, but current is not. And then when we look at when we're looking at current, we have a safety factor of 1.25 that we multiply by. So then our continuous current rating is going to be the short circuit current times 1.25. And short circuit current is the maximum current that module is going to put out if you have, basically you're shorting out the wires. That's the most current that module could put out under full sun conditions at standard temperature. So
safety modifier, is that just to get it under like a safe working?
So there are two factors here.
Space coverage is 1.25, so it would be a quarter of the way again for oversizing.
Let's see, and it's been a while since I've reviewed this, and I don't want to misspeak. The answer is I don't know.
Need to read this article.
Yes, read the article.
Yes, read this article.
And if you have a copy of the NEC, go back and look at it, because it'll talk specifically about why that factor. Because when we're sizing, we also go into more detail with looking at specifics for your location, and there are tables that you can look at it for the minimum possible temperature for your location. And I think that the 1.25 is based on that. It's kind of a given the coldest potential temperature that you'd see anywhere in the U.S., the most current over and above the rated would be about 1.25% of, or 125% of the production, or the output, the rated output. So that's just a safety factor to say, if it were a super freezing cold day and you had full sun condition, we wouldn't exceed this much. And then standard for most overcurrent, when you're sizing overcurrent protection devices, you usually oversize those by 25%. So again, you can either multiply times 1.25, or as they did here, they divide by 0.8 to determine the breaker size. So, and then they look at the next larger overcurrent device size. So then that gives you an idea of what your protection on your wire is. And then once you've determined what your wire is protected at, which here is 30 amps, now we need to make sure that the wire size is appropriate to handle 30 amps. because you want the overcurrent protection to actually protect the wire. So then you'll go back again to the NEC, and it gives you the references here, and you can look up, okay, given these conditions, what size is my wire going to need to be? And a lot of those things, and I don't know how much you need to go into depth for this class or for the NABCEP's entry-level exam. When you're doing the installer exam, you're given a scenario and you have to go through and make all the calculations. So the things that, you have to consider all the things that are going to affect the ampacity or the rating of the wire. Temperature is going to affect it, how many conductors you have in a raceway, how tightly packed they are is going to affect how much they can carry. And so that's basically what happens in this step 3 sizing conductor. It goes through what's the temperature going to be where the array or where these wires are, and there are different tables in NEC that help you figure out if it's in this size conduit, this type size conduit, if it's so close to the roof, what's the factor that you have to use. And so that's where they're getting these correction factors. You also need to make sure you're using wire that's rated for the conditions. Most of the time with solar, we use 90° C rated wire. We'll use a USE2, which is a service entrance wire, and it's rated for UV as well as high temperature and wet conditions. So that's kind of the standard. If you're putting it in conduit, you can go with a THHN or other options, but if the wire is exposed outside, you're going to see it USE. And there's some others. Now there's a solar wire that's specific to solar, but it's equivalent to the USE2. The solar wire, I think, has a higher voltage rating because some arrays are now going up to over 1,000 volts or up to 1,000 volts. They've raised the restriction on that. So again, what they're doing is they're looking at the temperature effect, they're looking at the fill or conduit fill factor there, and then they're multiplying all that out. Their continuous current, the temperature correction, the conduit fill, to figure out if the wire is adequately rated, and to handle the current that this would potentially produce. Like that would be the most you would expect it to ever see, and so it is. Let's see, up here, your breaker size doesn't necessarily take into effect these other variables, so it's a separate calculation. That's why you see the two different step 2 and step 3. And then we can talk a little about this. Let's see what else we have. So yeah, as they go through the calculations, then they refer you back to the table to figure out what size conductor is required. And then of the requirements, you have to use the larger wire rated. And so wires, I don't know if you guys are familiar with wire sizes and so forth, but as the number gets...
Transmission lines.
Transmission.
Yeah,
well, it's kind of like... yes, the smaller, yeah, the smaller the number, the larger the wire. So, and then you get into, once you get down to number 2, number 1, and then they'll go to aught. It's like a 2/0, 4/0, and so these are much bigger cables, battery cable size and bigger. But you'll see those in the tables in the NEC as you go down. You'll see the wire sizing change and the larger gauges of
So you
wires.
mentioned like DC towards the beginning here, it shows the gauge of the wire and the related resistance. Yeah, the resistance for the wire. So you're saying just to use aluminum for the mounting equipment? You also are those conducting wires typically aluminum, or is it copper?
The conductors are typically copper because they're much lower resistance than aluminum. And if you were using aluminum, then you wind up with a much larger wire. So, but it could be used in a system, and it just kind of depends on cost and if somebody has if you have something available that's aluminum, to be aware that you can't just interchange the two and just wire nut aluminum and copper together and expect it to work for you. So, you need to treat the wires and the connection. So, yeah, and then here in this article, or she, is this Justine Sanchez? Yep. She gives a reference to solarabcs.org permitting, and this is Bill Brooks' website, and he has a ton of good stuff in there, and he has some
Solar ABCs?
yeah, you'll see it in the article here in the last paragraph. He has some great things. I don't know if you have, I know in the past we had links to his website through the class site, but he has some really clear examples and worksheets and so forth to work through, and he has the tables very nicely laid out and available for the temperature corrections and so forth, or the temperature effects and so forth. So that's definitely a good resource to go to. And so when we're going through the sizing, we've got our array, we have to add up our voltage based on the number of modules in series. If we're combining, here we have a junction box and we're combining two arrays or two strings, and then we have to factor, okay, so now we've made this combination. Now not only have we had additive voltage by putting all these modules in series, but we've taken two strings and we've combined them together, and so now our current adds, so we've got twice as much current once you combine two. And some inverters you'll just combine out the inverter. Others have a high enough current tolerance you can plug in both. You can have combinations, combined strings that come in together. And so yeah, you have to go through the wire sizing process for the wires on the roof that would be exposed to sunlight. You have to factor wires that are in conduit that wouldn't be. You could potentially go into a combiner box and switch from the outdoor rated wires to something that can run indoors. Usually you're going to stick with a high temperature rated and a water resistant wire. But then once you get down below, you don't have the high temperature effects necessarily. And so if it's not going to be exposed to direct sun, then you have other options, and wires can be less expensive. And all of it is just sort of a game of optimizing. Does it make sense to switch here, to switch there? A lot of times we'll just use USE and run it all the way down because it's not worth adding a combiner box to change and to splice wires. But when you get into bigger systems, and if you're doing a lot more installations, it can make a difference. And so preliminarily, I'd say as you're just getting into it, If you wanted to do your own system, it's easier to just figure out the wire that'll work on the roof, and that'll typically work all the way down. So,
As a contractor, how often, like, how many other steps does it take you to figure out why is that?
well, it depends. It depends on the complexity of the installation, for sure. And if I have examples that I've already done, you know, if I've already used this inverter with this number of modules, then I've already done the calculations, and I can just go back and pull what I've done before, which makes it simple. And that's kind of my fault at this, or my flaw at this point, is not thinking enough about, oh, I didn't just do those calculations last week 4 times. So, and the other thing that I was going to say, you know, looking at this picture, this is based on a string inverter. And so this inverter is, you're taking the full voltage of the array, running DC all the way down to the inverter, and that's the only thing the inverter sees. More common installed these days are either microinverter systems or systems that use optimizers. So microinverter systems, a microinverter would be installed on the racking underneath each module, and the microinverters would convert the DC from each individual module to 240 volt AC and feed it into a trunk cable. That's an AC circuit that's 240 volts. So an electrician would run a 240 volt circuit out of the fuse box, out of the breaker box, up to the roof, and then the solar installer typically would take the electrician would also, and some solar installers are licensed electricians and they would do all this themselves, but if there's a, you know, if you're installing solar but not a licensed electrician, there are kind of different limits to what you can do. The cable that comes with these microinverters will typically be spliced into the house wiring, the 240 volt circuit, in a combiner box on the roof, and then that cable is rated to be outdoor. So it'll run, and you'll fasten it to the mounting system, and then you can plug the individual modules into these microinverters that then plug directly into that cable. So on an individual module basis, they're converting the DC to 240 volt AC, which is really neat, because then you can shade one module and it doesn't affect the array as a whole. When you have an array like this and you're tied to that string, and remember that low voltage number, if you shade 1, if you shade 2, if you shade 3, you know, if you have a shadow that's coming across, at some point you're not even going to have the voltage to run the system, let alone the production from the modules to make it worthwhile. So so you're kind of tied typically to the effect of one module when they're in a string like this. Whereas with the microinverters, as they become shaded, each one individually will drop off, but the rest will be fine. So
And that's standard now, you say?
it's very common now that people are using these microinverters. And then also the other thing is optimizers, which would connect with a grid-tied inverter such as this, but the optimizers look at the array as an individual module basis. And so they'll take the DC coming from the modules and they'll step it up to a level that is required to run the inverter. And then if ever there's a fault or a flaw, then the optimizers disconnect themselves, and thereby turning off your high voltage DC right there at the modules. It's done. It drops to 2 volt DC in the whole DC system, and you don't have an issue. With a system like this, if you don't have an accessible disconnect somewhere, then, I mean, we can look at what's our voltage. It says here 308 volts DC. So you'd expect 308 volts in these conductors coming down to the inverter, and nothing in between that you can do to disconnect that DC voltage. So that's kind of worrisome from my perspective. You know, you can turn off the inverter, but that doesn't mean that you've shut off the DC current coming, or the potential coming to the inverter. And then you can also, you might have at this junction box here that they show, you might have a means of disconnect, which would probably be a good idea. But still, up at the modules where the conductors come out of the modules, you've got that high voltage potential. So it's something you have to consider. Just because the inverter gets turned off doesn't mean your wires are safe, that your voltage has gone away. So usually with the AC side, you kill the breaker and everything downstream is off. But the inverter is being fed from the solar, so there's that to consider. So, and then typically you would an electrician who's trained in house wiring and so forth would put in the wiring on the other side and tie this to the existing system. There are limits or expectations with the breaker panel, and it's you are typically allowed to overload that panel by 20%. So if you've got a 100 amp panel, you can put in a 20 amp solar breaker over and above the 20 amp or the 100 amp feed from the utility. And the reason that is because you've got 100 amp potential coming from the utility and you've got 20 amp potential coming from the solar. You're required to fasten those breakers at opposite ends of the breaker panel, and so all current that's coming in, you would never be able to feed more than the 100 amp rating of that panel. Like, all that energy that's coming in is going to be dissipated and sent out on the different circuits before you had any one place on that panel that would reach over 100 amps. So yeah, the microinverters and the optimizers are much more common now, and they're a little more expensive, but they're a much safer way to do these systems, and I think we're going to see more things going that way in the future. Yeah, because high voltage DC is kind of scary. Can be. So anyway, we'll wrap up for now, and then I guess Brad will be back next week, and Naomi asked that you guys fill the NABCEP exam forms out as soon as possible. Get them to her or Brad next week, and then for anybody who's online, Naomi said that she would post these NABCEP exam sign-up material on Moodle, so keep an eye out for that. And thanks.